sharing a window?
Okay, I don't see that option when I click on present now. I just see an option of sharing the whole screen. Let me just.
Okay, I guess maybe it's device dependent, in which case we don't have a choice.
Okay, okay, maybe then I'll
Rohani,
just share the whole.
Gayatri, say.
Rohani, am I audible?
Yes, yes, yes.
Yeah. Have you logged in through Chrome?
No, it's Safari. Should I log in through Chrome?
No, yeah, log in through Chrome so that when you
Okay.
have the present now option, you have three options: your entire screen, a window,
Yeah.
a tab. Tab that's
Okay.
just for your videos and animation. So you just log out and then log in again from your Chrome.
Sure, I'll do that. Yeah, I'll just connect in
Yeah,
half a minute.
yeah.
Uh, I'm not seeing your. Are you sharing your screen?
Do you see something now?
Um, no. Yes, yes. Now I see your presentation. So let's wait for maybe 2 minutes to see if there are more
Sure.
people joining.
is there a chat option here that I can see? I logged in with my other device also.
Can you say it again, Ruhani?
So, is there a chat option that I can see? Is there something like that here?
Yeah, you should be able to type. In the side where you see the meeting, I think the layouts are different for everybody. I see a chat right next to people.
Yeah, it's an icon that looks like it's on the top ribbon right next to people. Yeah.
I'm going to find it out on my iPad because
iPad might be different. Yeah.
So do you need to use the chat, or we can go ahead without that?
Yeah, that's not
Should
important.
yeah. I guess if there are questions, I can stop
Sure.
you. Okay. So I think we'll get started. It's already 4 minutes past 4. So welcome everybody to another Institute seminar day seminar. And we welcome Ruhani Sharma, who's going to talk about reusing algorithms under conflict-free constraints. Welcome, Ruhani.
Thank you for the invitation. Yes, as Sushmita said, the talk is primarily about seeing whether we can reuse algorithms when we are encountered with some additional constraints, and particularly the constraints of conflict-free-ness will be of utmost importance to us. So I showing you this. So this is pretty much the kind of problem that we want to deal with in this talk in our own very little way. So typically, this is a problem that typically every algorithm designer faces. So a client comes up with a problem, and the algorithm designer spends days or years or sometimes even decades to try to come up with an algorithm that solves the problem. And then almost when the designer is ready with the solution, the client modifies the problem at hand. And this is probably unavoidable because the demands are growing with time. So this is something that's not really in our control. But what we are interested in is the following. So let's say as an algorithm designer, I design an algorithm to solve a problem. And now a client comes up with a constraint that does not really require change the problem at hand, but requires us to solve a problem with. So what we're interested in is the following. So suppose I have a solution that solves a particular problem, and then suddenly when someone asks me to give a solution to a problem with certain additional property, and that our efforts scale up in proportion to the additional property that is required. In an ideal world, we would want that since the extra condition is only an additive condition, we would want to be able to reuse what we have already developed for the original problem at hand, and then probably do some additional work to cater to the additional constraint that the client has put on us. Typically, more often than not, this is not the case. So the effort does not really scale up to the additive constraints. And in this talk, we're going to design some tool that allows us to reuse the work already done for a particular problem when an additional constraint comes into picture. So for the rest of the talk, I'm going to start with a problem, and throughout the talk, we'll try to design some algorithm, some good algorithm for the problem, and it's only towards the end of the talk that I'll talk about this reusability paradigm. So when we're trying to solve this problem, we'll design some tools, and we'll see how these tools can be used in general to reuse. They are encountered with certain kinds of constraints. So Now let me just start with a problem, and we'll see how to solve this problem throughout the talk. And the problem is by current events. So this is a problem that I call the virus control problem. So imagine a hypothetical world right now. We have a set of countries marked by these fictional flags, and there is a country which is marked by a virus. So let's say there is this country which is infected by a virus. We call this the spreader country, and then there is a country tagged fragile. So this is the country that is very fragile and cannot risk getting a virus. And other countries are more or less immune to the virus at hand. So this is the model that we have, and and our goal is to prevent the fragile country from getting the virus, from being infected by the virus. And the way the virus spreads in our model is the following. Suppose this country has the virus, and if this country allows travel to, let's say, this green country, and allowing travel is represented by putting a line between these two countries. If the country be green, then since the maroon country had the virus, we assume that if this travel is allowed, the green country also gets the virus. And so this is how the virus propagates. And one is not allowed to travel between every pair of countries, which is typically the case. So the countries which allow the pair of countries which allow travel to and from, they are represented by these. If I put an arc between two countries, it means travel is allowed to and fro these countries. And these relations are called edge relations. And typically such a structure which contains objects and a binary relation defining them in the form of these edges, such structures are called graphs. Model that we have, the model of the transport or the communication is represented by these edges. And we discussed how the virus spreads, and the goal is to prevent the fragile country from getting the virus. Fragile country can get the viruses, for example, since the spreader has the virus, we take this edge, fly to this country, and this gets the virus, and then we fly to this yellow country, and this gets the virus, and then we fly to the fragile country, and this gets the virus. So now, as a common consensus, all the countries decide to protect the fragile country from getting the virus, and they decide on following the following protocol. They decide on closing down of certain number of countries, such that once all the borders for these specified set of countries is closed, the virus cannot reach the fragile country. And because we want to do it in an economical way, we want to close borders of a minimum number of vertices, such that once I close the borders of those vertices, the virus cannot reach the fragile country. For example, in this case, if I close the borders of the countries marked with cross, it's not difficult to see that the virus cannot reach the fragile vertex, because if I close borders for these countries, so when I say close borders, I mean we close all inbound and outbound flights and from these countries. So when we close these borders, these disappear together with their connections, and now it's easy to see that if the virus is here, the virus can spread only to these countries and will never reach a fragile country. This is the problem at hand that we want to discuss. So in the next slide, let me just define the abstract model that captures this problem. So this problem is captured by a very classical problem in graph theory called the separator problem. The input is a graph G, and there are two vertices S and T. And the goal is to decide to find out the minimum number of vertices that can be deleted from the graph, such that it's not possible to reach T from S. This graph, 3 vertices, there is no way that I can reach T from S. And a classical and a fundamental problem in graph theory, and its solutions were known as early as early 50s, 1950s. one solves this problem via the concept of flows. So there is a celebrated result that associates the minimum SG separators in a graph with maximum SG flows in the graph. So a celebrated theorem says that a min cut or a min separator between a pair of vertices is actually equal to the max flow that can be routed between these two vertices. And just to quickly and informally define what a flow between two vertices is, so imagine that S vertex is a producer. There is a factory that produces something, and T is the consumer. And S wants to route, and these edges represent some pipelines via which the products will be routed, and each pipeline has a capacity. In our case, each pipeline or the edge has capacity 1. And the goal is to decide how many units of the produce can be routed from the producer S to the consumer T under the following conditions. So the conditions are that at no point do we congest the edges. So if the pipeline has unit capacity, at no point do we send more than unit produce along this pipeline. And then the second property is that there is no congestion happening. So, or in other words, vertices do not have any storage capacity. So if, let's say, 1 unit of product is routed through this pipeline, this unit product should come out of these, emanating out of these vertices. So this is very informally what the notion of an ST flow is. For example, in this example, if you see, if I route 1 unit of product through the yellow path and 1 unit of product through the green path and 1 unit of product through the pink path, the two conditions of no congestion and having to store produce at vertices is satisfied. And in fact, in this example, it can be shown that of product can indeed be routed in this graph. And as I said before, the celebrated theorem says that if one is able to find out what is the maximum amount of product that can be routed in this graph, that amount is equal to the minimum size of the ST separator. And so the ST separator problem basically boils down to finding max ST flows in the graph. And that can be done with sort of greedy-ish algorithms. I'll not go into the details of this. And this can be done quite efficiently. And in particular, this can be done in time, which is proportional to the number of edges. E represents the number of edges in the graph. And F is the maximum possible flow that can be routed in the graph. I'll later talk about why I call these efficient algorithms or why such kind of algorithms are good to us. But the moral of this slide is that the ST problem has solutions via flows. Now, the idea of associating flows with ST separators is a very elegant idea, and now this is the problem at hand. And now let's try and add some more constraints in the problem, and let's see if we can use the same ideas to solve this constraint problem. In particular, I begin by adding this constraint of outliers to the ST separator problem. So if I have to motivate this problem, let's go back to the virus control scenario. So there we assume that all the countries unanimously agreed to help the fragile country, and all the countries unanimously agreed that, okay, if we are asked to close our borders, we will close our borders, if that's the case. But in an ideal situation, that might not really be the case. There are always some outliers in any universe. So in particular, suppose a set of countries in the protocol, they really don't care about what happens to the fragile country, and they are not ready to close their borders, and that's where this problem comes into picture. So this problem is defined as follows. So as the previous problem, but now we also have a set of outliers, which is the set of vertices X. And now the goal is to delete a minimum number of vertices that are non-outliers. So now we're not allowed to delete the outlier vertices because they refuse to participate in saving the fragile district. So we can only delete the non-outlier vertices such that after their removal, the same thing happens. You cannot reach T from S. So constraint, and to be able to solve this problem using the ideas developed for the ST separator problem. And in fact, in this case, we are indeed lucky. For this special kind of constraint, the outlier constraint, we can indeed reuse the algorithm of the ST separator problem. And let me try to give you an intuition of why one can do that. So green vertex is an outlier. So in this figure, I've just drawn one outlier vertex just to convey the idea. So if this is an outlier, this vertex does not want to participate in district. In other words, it does not want to close its border, or it does not want to get deleted. But this vertex still provides connectivity between vertices, and or in other words, this vertex still can propagate the virus. So we just need to keep the information that these vertices get the viruses, and in which ways can it propagate the viruses. As we can keep this information, we can forget about these outlier vertices completely. And there's an easy way to do it. For example, look at the neighbors of this green vertex. So between any two, between any two neighbors, for example, look at this neighbor and this neighbor. These two neighbors can be reached via the green vertex. So in other words, if the virus has reached this vertex, then it can reach this vertex via the green outlier vertex. And we just need to remember that the virus can reach from here to here, in which case we edge between these two vertices. So for any pair of neighbors of the green vertices, we go and put an edge signifying that these two vertices can be reached via a green vertex, and then at the end we completely forget about green vertex. Note that by doing so, we have captured the information required to see how the virus can propagate. And since now we have deleted the outlier vertex completely, we can actually go and solve the ST separator problem on this graph. Kind of constraints, we can indeed reuse the algorithms that we have already set up for the ST separator problem. So we got lucky here. So let us remember that is easy for us. It does not make the problem harder. We can reuse algorithms here because we're going to use it later during the talk. So now let me talk about adding other kind of constraint of conflicts. So in this so to motivate this scenario, consider the following situation. Suppose now we decide on a set of vertices which needs to or we decide on a set of countries whose borders need to be closed, and now once these countries are decided, we leave it on these countries to unanimously come up with a protocol of closing their borders. And to be able to do this peacefully, we would want that these countries do not have conflicting opinions or do not have conflicts with each other. This problem can be modeled as follows. So we have this graph with black edges, which was the same as the previous graph. Now, additionally, we also have these kind of conflict edges. Pink edges representing conflict between two vertices. So if two countries have a conflict between them, we add this pink edge between them. And now we want a set of vertices such that in the black graph, when I delete those set of vertices, those vertices disconnect S from T. And in the pink graph, none of these vertices should have an edge between them. So for example, in this case, this red crossed solution is not a solution because there is a pink edge connecting these two red vertices. But this green solution is a conflict-free solution because there is no pink edge connecting green crossed vertices. So now we want such solutions, and it turns out that finding such solutions becomes extremely hard. So before that, just a formal definition of the problem would be, one can imagine as being given two graphs. One is the black graph, which is the connectivity graph, and one is the pink graph, which is the conflict graph on the same set of vertices. And the goal is to delete a minimum number of vertices, which the black graph disconnects S from T, and which in the have no pink edge between them. And as I said before, forget reusing the ST separator problem, ST separator algorithm for this problem. Even the ideas of flows do not seem to work to give solutions for this problem. And there's a fundamental reason why this happens, and the reason being the following. So P and NP complete are the holy grail of complexity classes in CS. So very informally speaking, P is the class of problems that which have algorithms whose running time is a polynomial function of the input size. Whereas for NP complete problems, we do not expect such algorithms unless something happens. And but for these problems, there is a polynomial time algorithm which can always verify a proposed solution. Having these two classes, what really happens here is that the ST separator problem and the ST separator with outlier problems lies in the P class, whereas the ST separator without conflicts problem lies in the NP class. So we don't expect a very good algorithm for this problem. In fact, forget about the ST separator constraint. Just asking for a maximum size is also NP complete. So now, just to motivate why we are so scared of this NP complete class. So we don't expect our algorithms whose dependence on the input is polynomial for these problems. In particular, for example, it's easy to see that these problems have an algorithm which has a running time of the form 2 power v, which corresponds to the algorithm that goes and check every possible subset of vertices and checks if this is indeed a solution. And this can be done in polynomial time. So just to highlight what changes so significantly when we go from polynomial time algorithms to exponential time algorithms, let's consider some concrete values and see how those running times behaves on those concrete values. For example, assume that we had a graph 1,000 vertices. So an algorithm that takes 2 power v times takes roughly around 10 power 300 instructions. And my quick Google search showed that the fastest supercomputer is roughly 10 to the power 17 instructions per second. This means to solve these 10 power 300 instructions, one will take roughly 10 to the power 227 years, which is insane. And just a fun fact, the age of the Earth is merely 10 to the power 10 years. So let us compare this with the algorithm that we had for the ST separator problem. So again, on the same sized input, this problem takes a microsecond to run on the fastest computer and roughly a second on your MacBook Pro. So that's why having exponential time algorithms for problems is highly undesirable, because the running times blew up even for very small values of input, which is like 1,000 in this case. If this is a scenario, let's see what we can do to circumvent NP-completeness. So one thing that one can do is that one can add the notion of budgets. Typically, when we are seeking for solutions, very rarely are we interested in finding minimum size or maximum size solutions. Typically, we have a budget at hand, and all we're interested in is whether the solution fits our budget. In the ST separator problem, let's say we also have a budget k, and we're interested in seeing if we can delete at most k vertices, which disconnects S from T. And on hand, one can improve the previous exponential running time slightly and get an algorithm which amounts to checking all k-size subsets of the vertex to find out if. And this is definitely a continuous algorithm, but it still takes some 10 million years on the fastest supercomputer. Just introducing the budget is not enough, and this is where we introduce the notion of fixed parameter tractability. And the notion of fixed parameter tractability is the following. For NP-complete problems, typically for NP-complete problems, in the realm of fixed parameter tractability, we analyze the running times of our algorithm on 2 clocks. So we analyze the running time of the algorithm. We analyze the dependence on the input of
Rohan?
Yeah.
You should try and finish in the next few minutes, so that you're aware of your time. The time. Sorry for the interruption.
So typically we're interested in running time, which depends exponentially on k probably, but only polynomially on the input size. So for example, some nice running times of this form would be this, which is linear in the input and to an exponential function of k. And for example, if you compare this kind of an algorithm with the 2-part k kind of an algorithm, this takes just a microsecond on the fastest computer. So now we're interested in designing fixed parameter tractable algorithms for this ST separator problem. And as it turns out that both these problems cannot be FPT unless again something bad happens. But what we can still show is that, so I'll be interested in the thing marked star. What we can still show is that the problem is tractable or is FPT when the conflict graph is planar or degenerate. So just to motivate the problem a little, planar graphs are graphs which can be drawn without the edges crossing each other, which can be drawn on a sheet. And these graphs are interesting because these graphs model the world map with borders. So if you have vertices representing the countries of the map and edges representing the relation saying that these countries share a border, then planar graphs can nicely capture these graphs. And hence, even if we allow our conflict graph to be a planar graph, this still captures a lot of problems because a lot of times conflicts happens with neighboring countries. So this is still a good enough result. And I'll just briefly tell what we can say about these kind of results. So planar, maybe just quickly. So planar graphs are a nice thing about planar graphs is that they are graphs which have a vertex of degree at most 5. And because every subgraph of a planar graph is planar, every subgraph of a planar graph has degree 5. Such graphs are called 5D. And what we show, let me skip this, what we show is that conflict graph is restricted to be a degenerate graph, the problem can be solved in FPT time. And the way we do it is the following. This is the most crucial tool that we have. So we compute a family of conflict-free sets in the conflict graph with the following property, that if you look at any at most k-size conflict-free set in the conflict graph, there exists some set in the family that contains it. So the family might not contain all conflict-free sets of the conflict graph, but they definitely contain enough sets such that any k-size conflict-free set is contained in this graph. And we call this family a k conflict-free covering family. And note that once we have this family, there is a very easy algorithm for the problem, which does the following: conflict-free covering family for the conflict graph. And now for each set X in the family, it solves the ST separator problem with outliers, where the outlier set is the vertex set minus X. Because we know that any conflict-free set is contained in some set of the family, so for every set X, we check if there is a solution lying inside the set. What happens here is that we have traded off the conflict-free constraints with the outlier constraints, and these constraints are much easier to tackle. And hence, for this problem, now we can reuse the algorithm of the ST separator problem with outliers here. So, having said that, just one last caveat is that we want to be able to compute this family in a nice time and of a nice size. And this is our main result. This is our main tool that says that if the graph is degenerate, then can be of this size. The size note, this is a size where the exponential dependence of the size is only in k and the degeneracy. It can be computed in the family of this size can be computed for degenerate graphs, and it can be computed in times proportional to the size. Main result, and the proof of it is very elegant, but I'll skip the proof that we have. So using this result, we can actually reuse the algorithm for ST separators with outliers to design an algorithm for ST separator with outliers. So now just one last comment about how we can use this tool to reuse algorithms for other problems. So you can think of your favorite problem and then compute a k covering family, conflict-free covering family for the conflict graph. And then for each set in the family, you solve your favorite problem with the outliers constraint corresponding to this set. And typically, as I said before, outlier constraints are easier to handle than the conflict-free constraints. And this tool allows us to the difficult things for the easier things. So using this tool, one can design problems and conflict-free versions of various problems, and by reusing algorithms for of the respective problems. But I'll skip defining these problems. And just the last slide, of conflict-freeness can be generalized for nowhere dense graphs. So right now we showed that there is a nice family for degenerate graphs. This can be generalized to something called nowhere dense graphs. And then I'll skip the defining all these things, but then there are natural barriers on trying to generalize the notion of conflict-freeness, especially for these notions marked in red. And there are, of course, a lot of scope of seeing what other kind of constraints can be captured by the kind of tools that we had. That's all that I had to say, and thank you for your attention.
Thanks, Rohani. Yes, Vani has a question, and I'm afraid we may not have time for more than one question. So, Vani, go ahead.
Rohan, thanks. It was a very nice talk. I think I understood at least a little bit. But I have a very general question about this. You started in the introduction that this question of asking, can you reuse an algorithm if additional constraints are put? Is there a theoretical way of knowing what should be the nature of this additional constraint put such that you can determine whether the algorithm can be used or not? Is there a way, a priori way to know this?
I would say no, because typically I think that is what I wanted to convey in my very first slide. When an algorithm designer is a problem, try to problem and depending on what ad hoc ways are used to design the problem, those define. I mean, it's we can go over these ad hoc ways and try to realize, okay, that maybe adding this constraint will not affect these ad hoc ways and so on. So as long as the process of algorithm design remains ad hoc, I don't think there is an a priori way of dealing with it. But having said that, there is a fair amount of meta theorems right now. So there is a fair amount of theorems that try to design algorithms for a large class of problems uniformly, like in a very systematic way. So for those kind of results, maybe you can. But typically, if the whole design procedure is ad hoc, one cannot.
Okay, all right, thank you.
So, thanks again, Rohani, for your talk. And the next speaker is Apurva. Apurva, are you ready?
Yeah, I know.
Okay. So maybe you can start sharing your screen then.
Yeah, sure. Are the slides visible?
Yes, the slides are visible. So I welcome the second speaker of the day, Apurva Biswas, who is going to talk about Mpemba effect in driven granular gases. And I hope I got the pronunciation of the first word right.
Yeah.
So yeah, welcome, Apurva.
Hi everyone. So I'll be talking about Mpemba effect in driven granular gases. So I will explain what is Mpemba effect and what are the known results in various physical systems and how to analyze this effect, especially in the case of driven granular gases. It has been done with Professor Rajesh along with Prasad and Oren. So let's consider plot where temperature is a function of time, and now we consider two systems P and Q, which are where P is initially at a higher temperature than Q. And now if we quench both the systems to a common equilibrium state where the final equilibrium state has a lower temperature compared to the initial conditions, then we see that the system P, which was initially at a higher temperature, relaxes to the final equilibrium state faster than Q. So this effect is known as the Mpemba effect. And this anomalous relaxation in temperature is different from the known Newton's cooling law, which is a quasi-static cooling. So if we consider the lower half of this plot, So this red trajectory shows the quasi-static locus. And now if we consider two systems, one at a higher temperature TH and another at a colder temperature TC, and now if they evolve quasi-statically to a final equilibrium state having temperature TB, then their trajectories won't cross and we won't be able to see the Mpemba effect. So it tells that Mpemba effect is essentially a non-equilibrium process. So now, starting from those two initial conditions, if they start to evolve along the trajectory shown by the purple and the yellow one, then we can see that the hotter system can cool faster than the colder one. Of water. So various reasons are known for the existence of such an effect in water, which includes evaporation, cooling, and hydrogen bonding, but they are specific to this system only, and in general they do not define such effects in other systems. The Mpemba effect is measured in terms of the time it takes to cool the initial temperature to the freezing temperature of water. So existence of such an effect in the case of water involves a phase transition, but we'll see that in order to define such an effect in other systems, it did not involve a phase transition. And also the quantity that is monitored here as a function of time is temperature, but it can be different for different systems. Like the second case, here the Mpemba effect is observed in magnetoresistance alloys, but here the analogous quantity to the temperature here is magnetization. So here the system which has a higher initial magnetization relaxes to a final equilibrium state faster than other initial conditions. And similar effect is observed in clathrate hydrates also, where we can see that if the initial temperature is higher, then it takes lower times to freeze. So in theoretical models, Mpemba effect has been analyzed, where the system undergoes Markovian dynamics. For example, in Ising model, three-state system, and in Fokker-Planck dynamics. But here the quantity that is monitored as a function of time is a distance from equilibrium function. So if we consider this plot, so here y-axis measures the distance from equilibrium of the various initial conditions. So here the trajectory shown by the red starts at a higher temperature and is initially at a larger distance from the equilibrium than the blue curve. But as it evolves in time, we can see that the red trajectory relaxes faster compared to the blue curve. And due to the presence of the Mpemba effect, various other interesting results are also observed, which involves exponentially faster cooling, and also the result that if there is a pre-cooling stage in the system, then it can lead to faster heating. And recently, such an anomalous effect has been observed in experiments also for colloidal systems which are immersed in water, and the water acts as a heat bath for the system. So the experimental results suggest the existence of exponentially faster cooling for certain initial conditions. So here in these plots, y-axis is the distance from equilibrium, which is measured as a function of time. And for certain initial conditions, like if we consider case 3, where the red trajectory is for the system which is initiated at a higher temperature, and the blue one is initiated at a comparatively lower temperature. And this is a semi-log plot. So the straight line for the red curve shows that it decays exponentially with a larger relaxation rate, whereas the blue curve decays asymptotically with a slower relaxation rate. Thus, it verifies the theoretical prediction made in the context of Markovian Mpemba effect. So such an anomalous effect has been observed in the context of driven granular gases also. So in this talk, we will look at various models of such non-equilibrium systems and how the effect can be analyzed. So let us first define the model for granular gas. So it is basically a dilute composition of macroscopic inelastic particles. So here the particles interact through binary collisions, and the collisions are momentum conserving, but due to the presence of inelasticity in the system, they dissipate energy. So these particles are supplied energy from external sources, and due to the interplay of this dissipation and the external supply of energy, they reaches a non-equilibrium steady state. Now, in order to analyze the Mpemba effect in such non-equilibrium systems, we define the granular temperature as the mean kinetic energy of the system, which is defined by this expression. And we will see in the various models that we will consider that the time evolution when calculated as a function, it will form a coupled differential equation with various other quantities. Like the first example as shown on the left, here the temperature T couples with the quantity A2. We will define these terms later when we consider the models. And the expressions on the right, here the temperature couples with another parameter theta. And we'll see that due to the presence of this coupling of the temperature T with other parameters, it ultimately leads to the existence of the Mpemba effect. So let's first consider the case of smooth granular gas. So in this model, we consider only the translational motion of the particles. So here, the translational kinetic energy is calculated as a function of time. And in this analysis, the velocity distribution function is approximated around Gaussian using Sonin polynomials. And this distribution function is put into the Boltzmann-Fokker-Planck equation, and the time evolution is calculated. And we see that the temperature T, which is nothing but the mean kinetic energies of the particles, couples with the parameter A2. So A2 is the excess kurtosis, or it is defined as the scaled fourth moment of the velocity distribution function. So the temperature T couples with A2 in this case, and let's see how it leads to the existence of Mpemba effect. So in this plot, the y-axis shows the temperature, which is plotted as a function of time. So let's first consider the first three plots on the upper half of this plot. And those three trajectories correspond to three different initial conditions for the temperature T and the parameter A2. So we can see that the blue curve, which is initiated at a higher temperature, relaxes faster compared to other initial conditions, which were initially closer to the final equilibrium state. And the lower half of this plot shows the existence of inverse Mpemba effect, where the system is heated instead of being cooled. So in that case, the red curve, which was initially at the lowest temperature, heats up faster than other initial conditions. But in this analysis, the velocity distribution, which correspond to the initial conditions of T and A2, are sampled from a non-equilibrium distribution, and it is not known how is their dependence on the intrinsic parameters of the system, so that they can be tuned to access these initial conditions. So we'll try to answer these questions in various other models for driven granular gas. So next we consider the case of rough granular gas. So here we consider both the translational and rotational degrees of freedom. So we can define both translational and rotational kinetic energies, and their sum gives us the total kinetic energy. We'll define it as the granular temperature. We can define another quantity theta, which is the ratio of the rotational to the translational kinetic energies. And in order to obtain the time evolution of the granular temperature, here we use a Gaussian approximation for the velocity distribution, and we put it in the Boltzmann-Fokker-Planck equation for the velocity distribution. And we see that the granular temperature T forms a coupled differential equation with theta. And let's see how it leads to the Mpemba effect. So here in this plot, y-axis measures the temperature as a function of time. And the three different trajectories correspond to three different initial conditions of the quantities T and theta. And the blue curve, which was initiated at a higher temperature, relaxes to final equilibrium state faster compared to other initial conditions. But again here, the initial conditions were not sampled from a steady state distribution. So we do not know what are the system parameters that govern these initial conditions. So here we present an exact analysis for the existence of the Mpemba effect in the context of inelastic gases. And we ask the question, if these anomalous effects are true, if we consider the initial conditions to be true steady states of the system, and what are the system parameters that govern these initial conditions. So here is the collision model that we consider. So here the particles collide at a rate which is independent of the relative velocities of the particles. So this is sort of a stochastic model of collisions, and the collisions are obviously momentum conserving, but due to the presence of inelasticity, they dissipate energy. Compensate for the loss of energy, the particles are driven at a rate lambda d. Here we model the driving as such by this form. This is a microscopic form of driving where Rw, the parameter Rw, signifies the decrease in velocity when the particles collide with the boundary that is added to the velocities. And this eta, we do not use any approximation for the noise distribution, and it can be taken from any arbitrary distribution with a finite second order moment. So in this model is called the Maxwell model, and in this model we'll consider two different cases. Dispersed gas, where we consider only one type of particles, and the other is the bidispersed gas, where two different types of particles constitute the system. And we will try to analyze the nature of the initial conditions for the existence of the Mpemba effect in both the cases. So let's first consider the case of monodispersed gas. So it consists of only one type of particles. So here the granular temperature is equivalent to the mean kinetic energy of the particles, and the exact analysis shows that the mean kinetic energy forms a closed coupled differential equation with the 2-point interparticle velocity correlation C, which is defined by this expression. And we analyze these coupled differential equations between E and C to analyze the existence of the Mpemba effect. Let's first define how to the Mpemba effect in this system. So suppose we consider two systems P and Q with these initial conditions for E and C, such that system P is initially at a higher temperature than Q. So the criterion for the existence of Mpemba effect is that after a finite time tau, the trajectory for the P, which was initially higher than Q, will remain below than that of Q after the crossing time. So with this criteria, we can derive the condition for the existence of the Mpemba effect in terms of the quantities E and C, and they are related to the system parameters, which are included in these terms lambda plus R11 and R12. So based on this condition, we choose a pair of initial conditions for the systems P and Q, such that P is initially at a higher temperature than Q. So here y-axis is the energy time, and we can see that the the initial condition for P, which was initially at a higher temperature, relaxes faster compared to Q. But in this analysis, we see that only non-stationary states can give rise to Mpemba effect. So we consider this case for bidispersed case, and we will see that benefit of using this model is that we can choose steady state initial conditions, and we'll see how the initial conditions are governed by the intrinsic parameters of the system. And so here it consists of two different types of particles, A and B, and both the particles are driven with different driving strengths. And in the steady state, the calculations show that all the interparticle velocity correlations between the particles goes to 0, and we get different steady state energies for the particles A and B. So here the total kinetic energy, or equivalently the granular temperature, is the sum of the kinetic energies of A and B, and it forms a coupled differential equation with the quantity E difference, which is the difference between the kinetic energies of A and B. So based on the criterion for the existence of Mpemba effect in the system that we just discussed, we can derive this condition for this model, where the initial conditions are related to the intrinsic parameters of the system. So based on this condition, we choose a pair of initial condition that shows the existence of Mpemba effect, also the inverse Mpemba effect. Here the system is heated instead of being cooled, and the system Q, which was initially at a lower temperature, heats up faster than system P. And here is the phase diagram for the initial conditions, which are measured as a function of the parameter RAB. So RAB is the coefficient of restitution between A and B type collisions. And this solid line gives the critical line, which is obtained from this condition. And all the initial conditions, phase space initial conditions that lies below this critical line shows the Mpemba effect, whereas the other region doesn't. And we can show that all the initial conditions can be generated by simply tuning the driving strengths that were defined for A and B type particles. So here we show that even steady state initial conditions, which can be controlled by tuning the system parameters, give rise to the existence of Mpemba effect. So here we present the possibility of the existence of strong Mpemba effect in the system, and strong Mpemba effect refers to the phenomenon where an initially hotter system, when quenched to the final temperature, relaxes at an exponentially faster rate. So if the time evolution is given by this expression, where it decays with different rates, lambda plus and lambda minus, and lambda plus is greater than lambda minus. And now if we set the coefficient k minus, which is associated with the slower relaxation rate, to 0, then we get the condition for the existence of strong Mpemba effect. So based on that condition, we choose the initial condition for the system P, which was initially at a higher temperature, whereas system Q doesn't satisfy the condition for the strong Mpemba effect. So in this plot, this is a semi-log plot where energy is plotted as a function of time, and we can see that the system P, which was initially at a higher temperature, relaxes exponentially with a single largest rate, whereas system Q decays asymptotically with the slowest relaxation rate as the time increases. Thus, bidispersed gas is a good candidate to observe the existence of Mpemba effect starting from steady state initial conditions. So till now we had considered a simple collision model where the particles were colliding at a rate which was independent of the velocities of the particles. So here we present a model for realistic collisions where the particles collide at a rate which is dependent on velocities, and here we show that merely a presence of anisotropy in the velocity distribution of the particles can lead to the existence of the Mpemba effect. So here is the model. Here we consider hard disks in 2 dimensions. So here particles collide at a rate which is dependent on the velocities, and obviously the collisions are momentum conserving, but they dissipate energy. So we apply noise to the velocities in order to compensate for the loss of energy. So here the driving is diffusive, which is a special case of the form of driving that we considered for the Maxwell model. The noise is Gaussian white noise. Here Chi naught square is the strength of the noise. Now, how do we introduce anisotropy in the distributions? So for that, we apply different driving strengths along the x and y directions of the plane, and we find that it gives rise to different steady state kinetic energies along x and y. Now, in order to analyze the time evolution of these kinetic energies along x and y, we use an anisotropic Gaussian form for the velocity distribution, having different variants along x and y, and we put this form in the Boltzmann-Fokker-Planck equation for the velocity distribution of the particles. Now, since we get a different values for the kinetic energies along x and y, we define the total energy as sum of these quantities. And we can similarly we can define another quantity which will be the difference of these two quantities Tx and Ty, and they form a nonlinear coupled differential equations. So we first linearize these equations in order to derive the condition for the existence of Mpemba effect. And for that, we choose first choose initial conditions which are close to a given final steady state, and we linearize those equations around the final steady state values. So we get a linear time evolutions, and with that we can derive the condition for the existence of the Mpemba effect, where the initial conditions are related to the system parameters by this relation. And using this condition, we choose a pair of initial conditions for the systems P and Q, where P is initially at a higher temperature than Q, and it shows the Mpemba effect and also the inverse Mpemba effect. And here we compare the linearized solution along with the complete solution, and they seem to match very well. The third plot is for the strong Mpemba effect, which shows that the system P can decay exponentially faster compared to system Q. And now the Gaussian approximation for the velocities that we had considered while deriving the time evolution equations is well validated from the results of molecular dynamics simulations. So here the dots represent the solutions obtained from the molecular dynamics simulations, and the solid line shows the complete trajectory obtained from the analytics, and they seem to match very well. So I will quickly summarize what we saw. So first we did an exact analysis for a simple collision model, which is the Maxwell model, and there we showed that for the case of bidispersed gas, we can see the existence of Mpemba effect and also the strong effect starting from steady state initial conditions, where conditions can be accessed by tuning the system parameters. And in the next study, we show that the presence of anisotropy in the velocity distribution can also lead to the Mpemba effect, where we did kinetic theory analysis based on more realistic collision. So these models can serve as a good candidate for the granular experiments which are still lacking in this field. So these are few of the references where one can analyze, study in detail for these effects. Thank you.
Thank you, Apurva. Are there questions for Apurva?
Sushmita, sometimes the questions are in the chat.
Okay. Okay, I didn't see that. Oh, yes. Vani, do you want to just ask your question?
Yes, yes. But generally, what is the protocol? Can we type the questions in chat? Do we disturb? It's not very clear to me. Or do organizers, when we type the questions in chat, do they read them? How does it work?
Uh,
Yeah, I can read the question.
Yeah.
Okay.
Yeah,
No,
I
no, no.
think
This
now
is,
we
this
can
is generic,
you
I
can go
think.
ahead and
Yeah.
we'll make it clear at the beginning of the talk so that there is no confusion next time.
Yeah. Okay. Thank you. So Apurva, so I just wanted to know, in general, is there any precondition, or does any system shows this Mpemba effect? Can you say a little bit about that?
From our analysis, we can say that whenever the quantity of interest that the system poses, like it can be temperature, magnetization, or any other quantity, if it is dependent on certain other parameters, then only we can try to ask the existence of the Mpemba effect, and then we need to choose the initial conditions accordingly.
No, I didn't particularly mean your work, but in general, when regarding Mpemba effect, like you showed water shows and other things, no? Is there anything that one can look for in the systems to see whether such an effect can be observed or not?
Yeah, like for other systems also, if you want to measure the temperature as a function of time, and if the temperature is dependent on other quantities, like in the case of water, the time evolution is also monitored by the hydrogen bonding.
Okay.
So in that case, if there is such quantities which also govern the time evolutions of the temperature, then we can ask the existence of the Mpemba effect in such systems.
Okay, thank you.
Like if the temperature evolves monotonically, then we can obviously cannot see the Mpemba effect.
Apurva, I have a short question.
Yeah.
In the case of water, as you said, people say hydrogen bond plays some role.
Yeah.
So what is analogous thing for granular media? I was just thinking, you have the notion of force chains. Do they play any role in explaining this phenomena?
So here in the context of granular media, so suppose we consider the monodispersed gas where only one type of particles are there. So in general, due to the presence of inelasticity, the equipartition is not there in the kinetic energies along x and y components here. So the total temperature, so we generally define the total temperature as the sum of these two quantities, Tx and Ty. But then we see that it is also governed by the initial difference between these two components, x and y.
So now my question was, whenever I hear about granular media, this very nice idea of force chains, some kind of emergent properties keep coming. So I was wondering whether you can explain some of this effect using force chain ideas, just a very vague thought.
Sorry, sir, I think I do not know about that.
Okay, fine. Thank you.
I'll look into that.
Are there more questions? So if not, we'll thank Apurva again and see you all next week.
Thank you.